Welcome to the last part of this practical introduction to Stochastic Optimality Theory and the gradual learning algorithm. In this lesson, we will use the OTGrammar file and PairDistribution file we created in order to train an OTGrammar. We will do this with the Praat program, and a necessary step, of course, is downloading it on your computer if you have not already done so. These two links lead you to the web pages where you can download either the Windows or Mac version. In this introduction, we will work with the Windows version. And once you downloaded Praat, you will see that it is an executable file that does not require any installation in order to use it. So we can get started directly. When you open Praat, this is the kind of interface that you should see, where you have the Praat, New, Open, and Save options at the top, and no other options to the right. The first thing we want to do here is loading the PairDistribution file and OTGrammar file. Simply select Open, and then read from File, and then look for these files in the directory you saved them in. Both will appear as objects in the Objects window. If you check the name of these objects, you can see that the files we prepared were successfully recognized as an OTGrammar file and a PairDistribution file by Praat. If you select the grammar object, you will have the option to view and edit to your right. By clicking on it, a new window will appear, and what you see here is actually a visualized version of the information we provided in the grammar file. All the constraints 1 to 4 are set to 100, and therefore we have two tableaus at the bottom where the constraints are still in an unranked state. In this unranked state, Praat will simply select those candidates with the least global amount of violation marks as optimal candidates. If we go back to the Objects window, we can also inspect our PairDistribution file. Select the file and then click on To Table. A table object will appear in the objects list. This table object has the same content as the PairDistribution object, only that now we can directly view it by clicking on View and Edit again. This will open a table window where you have a list of all of your input-output mappings as well as the relative frequency, which here is called weight. Once you checked your data and being sure that everything is as it should, we can start training. And the first step to do so is generating the training set. Select the PairDistribution file and choose the ToStrings option to the right. A new window will open where you can choose the number of training pairs or input-output pairs you want to generate. Praat will respect the frequency ratios or weights that are part of the PairDistribution file. In this class, we just choose 100,000 input-output pairs. Two new string objects will appear in the objects list, a string object for the inputs and another string object for the outputs. Select both of these string objects, which are now our training set, as well as the OTGrammar file, which is the model we want to train, and then select Learn to the right. The Learning window will open and you will see a couple of options, most of which should sound familiar to you if you remember the class on the mathematical basis of stochastic OT, like for example evaluation noise, which determines the standard deviation of the constraint functions, and plasticity, which determines how far constraint functions can be displaced at each learning step. There are also some options that we haven't talked about yet. Even though in the second class I said that plasticity is constant during training, relative plasticity spreading gives you the option of injecting noise into the plasticity value, which means that the plasticity or learning rate might show fluctuations during training. Number of choose refers to how often you want to feed each input-output pair to the algorithm as a training datum. Since we generated 100,000 input-output pairs and the number of choose is set to 1, this means that each input-output pair will be fed into the algorithm only once. Then you can tick or not tick the box Honor Local Rankings. If we had provided a constraint that we assume to have a universal ranking, for example one that we believe to always dominate the other constraints, we would have marked it as a local ranking in the OTGrammar file, and could have ticked this box if we wanted the algorithm to respect the local ranking. Respecting the local ranking then means that during training, said constraint will not be displaced. But since we didn't do this in our toy example, we could simply untick this box, or even leave it as it is because we did not provide any local rankings. Last of all, there's the option of choosing an update rule, which basically refers to what happens to the constraints in each learning step. As you can see, there's a plethora of options to choose from, but we will go with symmetric all, which corresponds to the update mechanism I explained in the second class. These are the parameters that we're going to use for our model. An evaluation noise of 2, symmetric all as an update rule, a plasticity of 0.1, relative plasticity spreading of 0.1, and only one chew. Once you set your parameters, you can simply click on OK, and the algorithm will train the grammar. Luckily, this process is really fast, so in no time the learning window will disappear, and if you go back to the objects window, it might seem as if nothing changed. But actually, the loaded OTGrammar file is now a trained grammar. An important thing to note here is that Praat does not make any changes to the files on your computer, so you should directly save the trained grammar as a text file and name it in a way that you can distinguish it from the untrained grammar. If you view the trained grammar, again by selecting it in the Objects window and clicking on View and Edit, you can see the trained model. Our trained grammar now has an actual stochastic constraint hierarchy, reflected in the ranking values that are marked in green here. These are then the most likely ranking points of each constraint function on the continuous scale. You will also get disharmony values, which are marked in red, which again is the result of adding random noise to the ranking values. The disharmony values or selection point values are then used to provide you the example tableaus for each input, which can be seen below. Note that in our case, the disharmony values have caused the tableaus to assume a ranking where C4 dominates C3, because C4 has a disharmony of about 108 and C3 has a disharmony of about 105. But if we look at the ranking values again, we can see that actually C3 is generally more likely to dominate C4, because C3 has a ranking value of 106 and C4 has a ranking value of 104. Looking at these values is important because it can help us make predictions about how the trained grammar will behave during the testing phase. If we look at the first tableau that has A as an input, we can see that the ranking of C4 dominating C3 results in B being the optimal candidate, because C and D already violate the highest ranking constraint C2, and the only other competing candidate A fatally violates C4. If we remember our PairDistribution file, we observed B as the output candidate in only 30% of the cases, while the other 70% of times, A was the optimal output candidate. For A to be optimal, C3 would have to dominate C4, because then B would fatally violate C3 before A can violate C4. In consequence, the ranking that produces A as the optimal candidate is C3 dominating C4. Given that we observe both outputs in the empirical dataset, these constraints and their respective functions should be relatively close to each other on the continuous ranking scale. And given that A is the more frequent output form, C3 should generally have a higher ranking value than C4. This can be seen above in the ranking value column, where C3 has a ranking value of 106 and C4 has a ranking value of 104. The fact that these values are so close to each other enables the two constraints to occasionally switch their ranking positions during evaluation. That's why this grammar will probably produce B as the optimal output at times if A is given as an input. I also want to mention that the ranking values for C2 and C1 are more distant from the other ranking values, which makes C1 and C2 very unlikely to change their ranking position during evaluation in this grammar. Now we want to put the trained grammar and our predictions to the test. Go back to the Objects window and select the trained grammar. Then select the option to Output Distributions. With this option, we will let the grammar generate a large set of input-output pairs, this time without the empirical information that we provided in the PairDistribution file. If the trained model was successful, then the input-output ratios of the pairs we are going to generate should match our empirical input-output ratios. A new window will open, and we will have to decide how many input-output pairs we want the grammar to generate. Ideally, we want to aim for a high number like 100,000, so that the ratios we are going to obtain next are not too skewed by random noise. Again, we provide an evaluation noise of 2. A so-called distribution object will appear in the object's window. Select the file and save it as a text file on your computer. When you open the file in a standard text editor, you can now see the results of the testing phase. Let's remember that in the empirical data, the input A produced A as an output 70% of times, and B as an output 30% of times, while the input B always led to B as an output. As you can see to the left, when provided with A as an input, our trained grammar produces A as an output about 68% of times, and B about 32% of times. As far as the input B is concerned, the trained model virtually reaches the 100% mark. And as we can see, the model can be called a success, because now we have a stochastic constraint ranking that is able to imitate the empirical input-output behavior, even though it overgenerates the A to A mapping and undergenerates the A to B mapping by just 2%. Certainly, one could start playing around with the learning parameters in order to get an even more accurate model, but this is something you should only be concerned with once you got the basics right. In conclusion, here's a list of steps that you want to follow in order to train an OT grammar in the Praat program. Load the OT grammar in the PairDistribution file. Generate a training set from the PairDistribution file. Select the untrained OT grammar and the generated strings. Select Learn and set your learning parameters. Inspect the learned grammar and save it on your computer. Let the learned grammar generate an input-output distribution and save the distribution as a text file. And now, the learned OT grammar and the distribution file are the results of your analysis. This is the end of this practical introduction, and I hope now you're able to construct your first stochastic OT analysis using the gradual learning algorithm. If you have any questions on the contents of this class, or if you want to have access to the materials, always feel free to contact me. And until then, thank you very much for watching.